We're about to apply Gauss's law to a conducting surface. So before we do that, we just need to discuss conductors a little bit and some of their properties and the conditions we're looking at. We're going to prove the first three of these items written on this slide here in this chapter, and we'll save the fourth one until we discuss potential. So the first thing we'll define is electrostatic equilibrium. That's an important concept. So electrostatic equilibrium is when there is no net motion of charge within a conductor. So static means still, and equilibrium means acceleration equals zero. In general, acceleration equals zero means constant velocity, which could be either zero or unchanging. But the word static means still. So this is what we're looking at here. So every charge in the conductor, so every charge is still, which means that the velocity is equal to zero. It's in equilibrium, so the acceleration is zero. So we're going to have to remember that the net force on every charge is the mass times the acceleration. It's going to be equal to zero. So this is what we mean when we say a conductor in electrostatic equilibrium. The properties that we're going to discuss are the fact that the electric field inside such a conductor is zero. The excess charge, so if there's a net charge on our conductor, it's entirely on the surface, or surface is. That's kind of interesting because you might think of it as only having one surface, but we'll see that it could have more than one. We know that the electric field just outside our conductor is perpendicular to the surface, and the magnitude is the charge density divided by epsilon naught. And then when we talk about potentials, we'll get around to showing that the charge density is actually largest where the curve is steepest. So objects that are pointy have large electric fields. Let's deal with our first property first, that says that the net electric field inside a conductor in electrostatic equilibrium is equal to zero. So that's our first property. First, let's think about where that comes from just by using the definition of electrostatic equilibrium. Remember, in equilibrium, the acceleration is zero, and the force, which is mass times acceleration, equals zero. Let's roll electric field into this. Electric field is the electric force divided by the charge, but the force is the mass times the acceleration. The acceleration is zero, so the net electric field has to be zero. So that comes from our definition of electric field. You can also take the contrary view. If the electric field weren't zero, then the net force wouldn't be zero, then the acceleration wouldn't be zero, and that would violate electrostatic equilibrium. So the electric field has to be equal to zero. And that's kind of easy to understand if there's nothing around. But what if we took our conductor and we placed it inside of an external electric field? So first, let's just make sure we understand what happens if there's no field anywhere. We would have charges in our conductor, and they're more or less just randomly organized. They're lying about any which way at all. So that's if there's no field. What if we introduce an external field? So we take this conductor and we place it in a field. We might put it between the plates of a capacitor, for example. So I'll draw that electric field. And that's an external electric field. It comes from something outside. So what would happen inside the conductor then? Well, first of all, the charges inside the conductor will feel a force. The positive charges will feel a force that's parallel to the electric field, and the negative charges will feel a force that's opposite the electric field. And the result will be, because remember charges can move around in a conductor, is that all of the negative charges will move to the left side of the conductor. That leaves the right side of the conductor having a positive charge. So they feel electric forces. The negative charges move opposite the field. Or opposite to the field. That results in a separation of charge. What happens if we have this separation of charge? Well, we have a bunch of pluses here, we have a bunch of minuses here. They're going to create an electric field inside the conductor. And since that's inside, let's call that E internal. So that separation of charge creates an electric field inside the conductor. It creates E internal. And then what happens is if we sum up those two electric fields, they sum up to be zero. That electric field cancels with E external. So our net electric field equals E external plus E internal equals zero. So even if there's an electric field all around outside, the total electric field is going to be zero. So now this is a result you're supposed to remember right off the top of your head. Anytime you have a problem that has a conductor in electrostatic equilibrium, you can say right off the bat that electric field is equal to zero inside the conductor. Next, we'll move on to our second property, which says that all of the excess charge will be on the surface or surfaces of the conductor. So if we have a conductor in electrostatic equilibrium and that conductor has excess charge, so it's not neutral, all of that excess charge will be on the surface or surfaces. So we're talking about a charged conductor and our conductor is in electrostatic equilibrium. So if we ask the question, what is the electric field inside the conductor? Then the first thing we can do is say that the electric field is equal to zero. And we know that's true because we just proved that was true. Well, next let's write down Gauss's law. Gauss's law tells us the net electric flux is equal to the integral of E dot dA. And that means we're doing the integral over some Gaussian surface. What kind of Gaussian surface will we choose? So let's make our Gaussian surface a line which is inside the conductor, really close to the surface. So this is our Gaussian surface, this red line right here. The solid line is the surface of our conductor. The red thick line is our Gaussian surface. So going back to Gauss's law, the integral of E dot dA over the surface we just drew is equal to Q enclosed divided by epsilon naught. So since our electric field is zero, the net flux has to be zero. If we put zero in here, the integral of 0 dot dA is still going to give us zero. So 0 is equal to Q enclosed divided by epsilon naught. That tells us that Q enclosed is equal to zero. No charge inside the Gaussian surface. So what is the next thing that we have to deduce? If we know there is a charge on the conductor, but none of the charge is inside the Gaussian surface, all of the charge must be outside the Gaussian surface. So the next thing we can do is let's take our Gaussian surface and let's push our Gaussian surface right up against the edge. So our Gaussian surface is close to, so close it's practically at, the surface of conductor. So we can take that Gaussian surface, so it pushes right up against the surface. That means that all of the charge on the conductor is outside the Gaussian surface or on the surface of the conductor. So that's our second property. You can also think of this in terms of physical properties. So we know that like charges feel a repulsive force. They want to spread apart. So if you have charges on a surface, they want to get as far apart as possible. The only way to get really far apart is to go to the surface. So we won't have two charges sitting in the middle close to each other. We'll get one charge over here, one charge over here. They'll spread out as far as possible. To do that, you've got to get to the surface. Some people liken it to cats in a room. So they always want to get far apart. They'll go to the opposite corners. So here's an interesting question. I'll bring up kind of a neat application. What if there's a hole inside of our charged conductor? What's the effect of that? And actually, why don't I play you a demo video first, and then we'll come back and make some notes.
Okay, to talk about electric shielding, I have a volunteer.
Hello.
And a cat close by. So this is a try this at home physics. What you need is a cell phone and a friend. Also tin foil, but we won't get to the aluminum foil just yet. So to begin our demo, Mary Honey, will you please call my phone?
Can do.
Takes a moment to get through. So you can see my daughter is calling me. Hopefully you can hear it. You can probably see the edge of the cat crawling on my desk. Okay, now the next thing you do after you try it is, I'm sorry, working from home is such a disaster. It's no less true for you than it is for me. So grab your aluminum foil, tear off a fairly large sheet, and wrap up your phone in the foil. So I've got my phone and I'm wrapping it up. Okay, now ask your friend to call you again.
Hi, this is Kelly. Please leave a message. At
So
the tone, please record your...
What happens is that the signal can't get through the tinfoil. The tinfoil makes what's called a Faraday cage. We can't get any net electric field inside. So the electric field inside a conductor is zero. Your cell phone operation depends on electric fields. No field, no function.
Okay, so hopefully you did that demo on your own. Please, by all means, pop over to the discussion groups and discuss it if you did. So now let's talk about what happened. So the tin foil or the aluminum foil was the conductor, and I put my cell phone inside that conductor. So there was my phone. And when we think about what happens is that all of the excess charge would go to the surface of the conductor, and the net electric field, let's see, all of the excess charge, let's just kind of quickly recap what we did. If I draw a Gaussian surface inside the surface of my conductor, my electric field inside equals 0 and the charge inside equals 0. So those are a couple of things that are true about conductors. Electric field being 0 is true inside the heavy metal of the conductor itself, but it's also true inside the hole inside the conductor. E is equal to 0 inside there too. So the electric field around my phone was equal to 0. This is an effect called shielding. If you've ever been in a place where your phone signal dropped, this is more or less what's happening. The electric field can't get through for whatever reason. And if there's no electric field, then there's no electric signal, and your phone can't pick up that signal because it's not getting to it. So you lose your phone signal altogether. Now, this has lots and lots of different places where we use it as applications. So if you've ever gotten a CAT scan done, that room would have been heavily shielded, or an MRI, because you don't want external fields messing with the results of your CAT scan. So CAT scans or MRIs, so medical applications. Maybe you have an RFID wallet. Some people do carry those around. That's so that nobody can copy the magnetic stripes on the back of your visa. So the signal from your visa can't get out, so nobody can copy it. What else? If you've ever shipped electronics from Amazon or wherever, it generally comes in what they call a static bag. So that's exactly the same thing. So shipped electronics. It comes in some sort of little foil pouch, which is the same as my sheet of aluminum foil, so that it doesn't get damaged by any stray electric fields as it's being shipped. What else? Some auditoriums do it. Some universities say that they do it with their exam rooms. I'm not sure. Maybe it's true, maybe it's not. Exam rooms. Computer rooms. Computer rooms would always be shielded because you don't want to get those zapped by external fields. And that external, the conductor, we call that a Faraday cage. So if you want something to be protected from an external electric field, what you do is you put it inside a conductor, and that conductor is called a Faraday cage.